Welcome to Pre-Calculus. Today we will investigate how to apply linear and angular velocities to real-life questions. We'll take a look at three examples. Our first example is about the Earth rotating. So the Earth rotates through one complete revolution every 24 hours. Since the axis of rotation is perpendicular to the equator, you can think of a person standing on the equator as standing on the edge of a disk that is rotating through one complete revolution every 24 hours. Using that information, we want to find the angular velocity of a person standing on the equator. So what we want to do is, first of all, decide which equation is going to help us put the information we've got together to find angular velocity. Just to get our three equations before us, we have one that's about linear velocity. So let's write that one. Linear velocity we would call v, and it's equal to the distance that an object travels in a circle, so it's arc length s divided by time. We also have an equation that helps us to calculate angular velocity. And angular velocity, we had given the label omega, and it's equal to the central angle theta divided by time. And then we had a result that is a bridge between linear and angular velocity. So we would just say this is linear and angular velocity. And the way that that equation went is it says that the linear velocity v equals the radius times the angular velocity omega. So those are our three essential equations when we're talking about linear and angular velocity. We just need to decide which one's going to be useful to us with this question. So first of all, I note that in the question, we're looking for angular velocity. So immediately that tells me that I need to pick up the angular velocity formula. It's either that one or the linear and angular velocity, but I think our information matches this middle one better. So I'm going to pull the formula. It's omega equals the central angle theta divided by time. And we just need to fill in or substitute for those two values on the right. So the central angle is given with this phrase, one complete revolution. So I need to think if I'm on planet Earth, and you can think we're looking down on the Earth, this would be the North Pole. And the equator is the actual circle. So we got a person standing there on the equator, very happy. And we're considering a full rotation. So a full rotation around the planet, really around any circle, is going to have a central angle of 2 pi. So I'm going to place that as my central angle, 2 pi, divided by the time. So the time that's given here is 24 hours. So once I've got that substituted in, basically that is my angular velocity. I just need to simplify. So I'm going to divide 2 pi and 24. And I can divide 2 out of both 2 and 24. What that's going to give me is pi over 12. And since this is in radians, I'll put radians per hour. And that really works well for us for this question. So looks like we did a good job selecting that middle formula for this first example. Let's take a look at our second example. Our second example is about a mixing blade. So here a mixing blade on a food processor extends 3 inches from its center. If the blade is turning at 600 revolutions per minute, we want to know what's the linear velocity of the tip of the blade in feet per minute. So I'm going to bring those three equations that we had from our first question, and we just, again, need to decide which one is going to serve our purposes with this specific example. So different from our first example, here I want to know linear velocity instead of angular velocity. So initially what I would say is I need that first equation. Again, it could be possible that we would use the third one, but again, it's good to just see, okay, maybe I can use this first one. So linear velocity here, if I'm going to pick up the first equation, I would need the arc length and the time. And just looking at what I've got, I don't have either of those pieces of information. So the other thing I could consider is if it's not this first formula, perhaps it's the second one. So let's kind of regroup and take the equation there in red that relates linear and angular velocity. So that one says that linear velocity is equal to the radius times the angular velocity. So I think we're in luck here. If we think about this situation, the radius is given by this 3 inches from its center. So I don't know what a mixing blade looks like. Probably something like this, but it's definitely turning in a circle. And so if that mixing blade extends out 3 inches from the center, that in fact is the radius. So I've got one piece, I've got the radius. The other piece I would need to calculate linear velocity here is the angular velocity. So I just need to look at the other information I've got. So I know it turns 600 revolutions per minute. And that's pretty close to angular velocity. Let's just say what we would need to fully convert that. So angular velocity I see is theta divided by time. So if it's turning 600 revolutions every minute, I know the time is 1 minute. So it's going to be 600. This needs to be my central angle in the numerator. So 600 times it's going around the full circle. So the full circle, like in our first example, is a central angle of 2 pi. So that would give me 1200 pi radians per minute. And that looks pretty promising because that in fact would describe our angular velocity. So I think we're good to pick up this third formula. So let's substitute our values in. So again, I'll just write it first. It's velocity equals radius times angular velocity. But I need to note that the units that I want to write my answer in at the end is not inches per minute, but feet per minute. So before I plug in my radius measure here, I need to convert 3 inches to feet. So I'm going to take that 3 inches, and the way to convert these is using the idea of cancellation. It's the same thing we used when we converted between degrees and radians. So I'm going to write, I know I need to go to feet, and I know I need to cancel inches. So I put inches in the denominator so I'll have a cancellation. And then I just need to make an equivalency. 1 foot is equivalent to 12 inches. So here I would cancel the inches. Turns out 3 inches is equivalent to 3 over 12, or 1/4 of a foot. So with that conversion, I'm good to now substitute into my formula. So my linear velocity here is going to equal 1/4 of a foot times the angular velocity, which is 1,200 pi radians per minute. So that's all set up. All I've got to do now is reduce and simplify. So at this time, I notice that my feet here is going to stay. Radians is going to fade away. Again, radians is kind of a unitless measure. It's for an angle, but it's not like degrees where it actually has a unit. So then I'm going to really multiply 1/4 times 1200. So that's like 1200 divided by 4. And that's going to equal 300 pi feet per minute. And that finalizes that answer. So again, for this question, we ended up having to use two of our formulas. We ended up having to use the linear and angular velocity. Along the way, though, we did have to pick up and use the angular velocity formula. Let's take a look at one final example. So our final example is about a Ferris wheel, the Riesenrad, or the Great Wheel. Was a Ferris wheel built in Vienna, Austria in 1897. So the diameter of this wheel is given as 197 feet, and one complete revolution would take 15 minutes. We want to find the linear velocity of a person riding on the wheel, given in miles per hour. So I'm going to highlight that miles per hour since that's our final unit measure, and we'll round it to the nearest hundredth. I'm going to start off by drawing a diagram of a Ferris wheel. I hope our Ferris wheel doesn't look like that circle. Okay, that's a little better. So I want to make some markings here. The diameter that's given to us is 197 feet. So remember, diameters from one side of the circle to the opposite side. And we just know for us, we're never going to need the diameter with linear or angular velocity. We need the radius. So I'm going to divide 197 into 2, and what that's going to give me is 98.5 feet for the radius. So from the center of the circle to the circle itself, that's the radius. So let's again put our three formulas kind of in view here so that we can decide which one or multiple of them that we need to pick. So I know I'm looking for linear velocity, so I could either choose the first or the third, the purple or the red. And again, like our previous example, I'm seeing that I've got the radius, so it really pushes me into choosing this third equation, the one that relates linear and angular velocity. So I'm going to set it up. The linear velocity, which we're looking for, is equal to the central angle. Oops, let me back up. It's equal to the radius, which we've got, times the angular velocity. So I see that I need angular velocity to make this formula work. So like our previous question, again, I need to go back to angular velocity and find that before I can find linear velocity. So to set up our angular velocity for this situation, we're going to say we need the central angle. So I see that this piece of information from our question is going to give us what we need, one complete revolution. So that's 2 pi. Again, one complete revolution of any circle is 2 pi radians. And it's going to be divided by the time it takes, 15 minutes. So in terms of these units, it's going to be 2 pi over 15. And our units are going to be radians per minute. I should probably put the actual number instead of just minute. So I'll fix that. There we go. So I've got my information. I know my radius is 98.5 feet. I know my angular velocity is 2 pi over 15 radians per minute. But before I plug stuff in to my linear velocity formula here, I need to convert so that my units are correctly miles per hour. So for miles, I see that that's a conversion that I need to make with my radius. It's currently given in feet, so it's 98.5 feet. So I need to multiply by a conversion factor that would give me miles instead of feet. So again, I'm going to set up the conversion factor so that the unit feet cancels and miles is the new unit. And I see that 1 mile is given by 5,280 feet. And that's just something that I could look up as a fact. 1 mile is made up of 5,280 feet. So I want to make that conversion here. So I'm just going to divide 98.5 by 5,280. And that's going to give me 0.0187 miles. So that's correct now for my radius, and I'm going to start plugging in. So the linear velocity is going to be equivalent to 0.0187 miles times the angular velocity. So there I need to make sure I'm in the correct units for time, and I'm not. It needs to be miles per hour, and the time frame that I've got is minutes. So what I need to do is something similar to what we did here with my conversion with feet to miles. I need to convert minutes to hours. So I'm going to take 2 pi over 15 radians per minute. And I see that my minute's in the denominator in that unit. So I need to multiply by minute above and hour below. And I need to put a 1 hour to every 60 minutes. So in terms of units, minutes are going to cancel. They're on opposite sides of the fraction. And then I see I got a cancellation here. 60 divided by 15 is going to leave me with 4. And so for my angular velocity here, I'm going to get 2 times 4 is 8. And then I had a pi. And I don't have any other values except for ones in my denominator. I can then put my units radians per hour. And that's now ready to plug in alongside my radius. So I'm going to plug in 8 pi radians per hour. And at that point, I'm good to go. I see I got miles, radians again, as a unit fades away. It's going to be miles per hour. So I just need to multiply what's 0.187 times 8 pi. So I'll just use the calculator to make that estimate. Again, I see I need to round to the nearest hundredth. So 0.0187 times 8 times pi. And that's going to give me a big approximation. I only need the first two values to the right of the decimal, so 0.47 miles per hour. So a very similar strategy that we used here in number 9 as what we used in the previous example. We had to use 2 of these formulas, the linear and angular velocity, the bridge formula, and also the angular velocity formula, along with unit conversions. Well, thank you for joining for this investigation of how to apply linear and angular velocity to real life questions. See you soon.